Hey everyone, this is Skeptical Alone, your feeder for astronomy videos. Today, we are going to talk about the world's most advanced telescope, the James Webb Space Telescope, JWST, and how it is able to capture the images of clusters, galaxies and stars that are billions of light-years away from us. So, let's begin.
Yeah, the James Webb Telescope.
James Webb Space Telescope.
James Webb Space Telescope.
The James Webb Space
James Webb Telescope.
The James Webb Space Telescope, JWST, is a space telescope launched on the 25th of December 2021 with the help of Ariane 5 ECA rocket, SN 5113, Flight VA256, from Guyana LA3. In January 2022 it arrived at its destination, a solar orbit near the Sun-Earth L2 Lagrange point, about 1.5 million kilometers, 930,000 miles, from Earth. The telescope's first image was released to the public on the 11th of July 2022. The James Webb Space Telescope designed to conduct infrared astronomy. It is the largest telescope in space, and is equipped with high-resolution and high-sensitivity instruments, allowing it to view objects too old, distant, or faint for the Hubble Space Telescope. This enables investigations across many fields of astronomy and cosmology, such as observation of the first stars and the formation of the first galaxies, and detailed atmospheric characterization of potentially habitable exoplanets. The telescope is named after James E. Webb, who was the administrator of NASA from 1961 to 1968 during the Mercury, Gemini, and Apollo programs. Webb's primary mirror consists of 18 hexagonal mirror segments made of gold-plated beryllium which together create a 6.5-meter diameter, 21 feet, mirror. This gives Webb a light collecting area of about 25 square meters, 270 square feet, about 6 times that of Hubble. Webb observes a lower frequency range, from long wavelength visible light, red, through mid-infrared, 0.6 to 28.5 micrometers. The telescope must be kept extremely cold, below 50 K, minus 223 degrees Celsius, minus 370 degrees Fahrenheit, so that the infrared radiation emitted by the telescope itself does not interfere with the collected light. Its 5-layer sunshield protects it from warming by the Sun, Earth, and Moon. The mass of the James Webb Space Telescope, JWST, is about half that of the Hubble Space Telescope. NASA, ESA and CSA have collaborated on the telescope since 1996. Development was managed by NASA's Goddard Space Flight Center in Greenbelt, Maryland, with John C. Mather as its project scientist. The primary contractor was Northrop Grumman Aerospace Systems, responsible for developing and building the spacecraft element. The James Webb Space Telescope has 4 key goals: to search for light from the first stars and galaxies that formed in the universe after the Big Bang, to study galaxy formation and evolution, to understand star formation and planet formation, to study planetary systems and the origins of life. The Space Telescope Science Institute, STSCI, in Baltimore, Maryland, on the Homewood campus of Johns Hopkins University, was selected in 2003 as the Science and Operations Center, S&OC, for Webb. JWST observations substantially advanced understanding of exoplanets, the first billion years of the universe, and other astrophysical and cosmological phenomena. Now we talk about how JWST able to capture the images of distant galaxies and stars. Imagine a camera so powerful it can see light from galaxies that formed more than 13 billion years ago. That's exactly what NASA's James Webb Space Telescope is built to do. The James Webb Space Telescope, JWST, is able to capture images of distant galaxies and stars primarily by using a large, gold-coated mirror and highly sensitive infrared instruments while operating in an extremely cold environment in space. Infrared optimization. The universe is expanding, which stretches the light from the most distant, earliest galaxies from shorter visible wavelengths into longer infrared wavelengths, a phenomenon called cosmological redshift. Webb is specifically designed to detect this faint infrared light, acting as a time machine to view objects that formed over 13.5 billion years ago. Massive light gathering mirror. Webb's primary mirror is 21 feet, 6.5 meters, across and made of 18 hexagonal, beryllium segments coated in a microscopically thin layer of gold, which is excellent at reflecting infrared light. This massive size gives it 6 times the light collecting area of the Hubble Space Telescope, allowing it to gather the incredibly dim light from faraway objects. Extreme cold environment. To detect the faint infrared signals from deep space, the telescope and its instruments must be kept extremely cold, around -370 degrees Fahrenheit or -223 degrees Celsius for most instruments, and even colder for the mid-infrared instrument, MIRI. The telescope's own heat would otherwise interfere with the observations. Giant sunshield. A 5-layer, tennis court-sized sunshield blocks heat and light from the Sun, Earth, and Moon, passively cooling the telescope's mirrors and instruments. Specialized instruments. Webb houses 4 primary science instruments within its Integrated Science Instrument Module, ISIM, that convert the collected infrared light into digital data. Near-infrared camera, NIR-CAM. The primary imager for the 0.6 to 5 micron wavelength range, crucial for detecting the first galaxies and stars. Mid-infrared instrument, MIRI, detects longer infrared wavelengths, 5 to 28.5 microns, which helps scientists see through dense dust clouds to observe star and planet formation and study cooler objects. Near-infrared spectrograph, NIR-SPEC, analyzes the light spectrum of up to 100 objects simultaneously to determine their physical properties, such as chemical composition, temperature, and motion. Fine guidance sensor, near-infrared imager and slitless spectrograph, FGS, NIRISS. The FGS ensures the telescope remains precisely pointed at its targets, while NIRISS has specific modes for exoplanet detection and characterization. The detectors in Webb's cameras convert the infrared light into digital data, which is then transmitted back to Earth. Scientists and image specialists process this data, assigning visible colors to different infrared wavelengths to create the stunning, full-color images we see, helping us visualize and interpret the structure, age, and composition of cosmic objects. These all instruments like mirrors, cameras and shields make it world's most advanced telescope till date, that is used to reveal truth beyond our imagination. That is how it works for us. Thank you for watching this informative video.